Hello and welcome. Today we're going to be doing an example of Fourier series calculation, and we're also going to be doing some analysis on it, especially like analyzing the roots, or basically the zeros of the function. So the function we're going to look at is the one that I've have it plotted right here. I've actually plotted it twice. Once is f of x by itself, it's the black line, and then f hat, of course, is going to be its Fourier series. And of course, the line is right over the top. Maybe I can even focus in on that to see it a little clearer. So this is sort of a V-shaped function. One thing to note about it, if you look at it closely, there are 2 points where f of x is equal to 0. One of those points is actually pi over 2, and the other one, of course, right there is negative pi over 2. All right, and it's an absolute value function, right? So it has a V-shaped look to it, and of course we're on the domain x from negative pi to pi. Okay, so if this is our example, what I want to do now is see about, let's actually look at those roots just very quickly. If I actually put pi over 2 plus or minus pi over 2 in there, of course I'm going to get a pi squared over 8 minus pi over 4 times pi over 2 coming out of it, which of course is going to equal to 0. So yeah, that's exactly what happens. All right, so what I want to do is compute the Fourier series. Another note that I'm going to make is this is, of course, is a even function. And that means, of course, we're going to get a cosine only series. Okay. And another note is if I actually look at the graph of this function, there is the x-axis there. You can see, of course, that the area under the curve over the whole thing is going to be 0 is going to be the total area under the curve. To verify that fact, so of course that implies, of course, that the first coefficient of the Fourier of the cosine only series is going to be 0. To see that, all we have to do, of course, is integrate from negative pi to pi. Divide by 2 pi, because that's always the formula, times pi squared over 8 minus pi over 4 times the absolute value of x dx. But because there's this symmetry, I can really actually just look at 1 over pi, and then integrate from 0 to pi of pi squared over 8 minus pi over 4 times the positive x, so we can remove the absolute values at that point. And it's quite easy to see here that the area under the curve of this function is going to be pi squared over 8 times x. That's the antiderivative, pi over 4x squared over 2. And then we evaluate it 0 to pi, and we end up with what is very clearly 1 over pi times pi cubed over 8 minus pi cubed over 8, and we get 0. So that verifies that the first Fourier coefficient is 0. So what we're looking for here then is our f hat for our Fourier series. The only thing left over to compute then is going to be n starting at 1, because we know our first coefficient is nothing. We're going to go up to forever, and it's going to be an times cosine of nx. So the next question then is, what are the n's for that? All right, so let's go to the next page to do this one. I'm going to write my function again. F of x is equal to pi squared over 8. minus pi over 4 times the absolute value of x. You might be wondering why I chose these particular values there. And the answer, of course, is it makes a n work out nice. It has a nice final answer. So I'll show you what's happening there. So we know our formula, an, is going to be, an is going to be equal to 1 over pi, the integral from negative pi all the way to pi, of pi squared over 8 minus pi over 4 times the absolute value of x, all multiplied by cosine of nx dx. But I'll again note here, of course, that this is an even function. And that, of course, is even as well. So the product, of course, is also even. In which case, we can truncate our integral that we're going to move over. We can actually use one integral, and we're going to double the value of it. We're going to go from 0 to pi. And just note that the negative pi to 0 integral will be exactly the same. So we just duplicate it. And that will be pi squared over 8 minus pi over 4. And now, on this interval, we can take off the absolute values and just have x there times cosine nx dx. Okay, now we're looking much, much better. We're going to continue on and calculate this. So we have that 2 pi out front. And now, of course, I'm going to have to distribute in to get two different integrals here. 0 to pi, we're going to integrate times pi squared over 8 times cosine of nx dx. Minus, and we'll move the pi over 4 outside, the integral from 0 to pi of x cosine nx dx. The first thing to note, of course, is that if I look at this integral straight away, I can see, again, we'll put their 2 over pi out front. We'll leave that there. I'll bring the pi squared over 8 out, and note that the antiderivative cosine, of course, is sine, but then because of the nx inside, I have to divide by an nx and then evaluate at 0 to pi. In this particular case, of course, we evaluate sine at 0 or pi once we put it in there. And, of course, we get nothing coming out of that. So we've gotten rid of one of our integrals, and now we have, I'll do minus, and then we're going to have, of course, I'm going to distribute in the 2 over pi there. I'm going to end up with a 1/2, the integral from 0 to pi of x cosine nx dx. Right, and again, all of this stuff right here is just 0. The next step, of course, is to use integration by parts. Okay, so we have that negative 1/2. And now we're going to take the cosine function and take its antiderivative. And so we're going to, of course, get x times sine nx over n. And we're going to evaluate that at 0 to pi, just like we did before. And then, of course, we have to subtract, but because we already have a negative there, we're actually going to add. We're going to have that 1/2 go there. And we're going to take the integral from 0 to pi. And, of course, we've taken the antiderivative of the cosine function, and now we take the derivative of x, which leaves us with 1. We're going to end up with a sine nx over n dx. Okay, we're almost done. And yet again, we're going to see when I plug in the pi in there, and a pi in there, and a 0 in there, and a 0 in there, everything is going to go to 0 again. And all we're left with then is this final thing to integrate. And I think we have it here. So my an is going to be 1/2. And now we do this integral. The integral, of course, is going to be the antiderivative of sine, which is going to be negative oops, it's going to be negative cosine of nx, and then of course the internal function of nx, we're going to get an n squared now, and then we're going to evaluate at 0 to pi, just like before. Okay, cool. Now we're going to do the evaluation. We have that n squared down there, and now up top, maybe I'll clean that up a little bit. We have an n squared down below times a 2, and then of course we're going to get a negative cosine of n pi minus a minus, which makes a plus, 1. All right, if I actually look at this function, look at this, we know that of course this is just going to be negative 1 to the n times negative, times a negative 1. All right, or the other way to write it, of course, is negative 1 to the n plus 1. All right, so we know for n equals 1, we're going to get a positive 2. So we'll get so for n equals 1, we're going to get a 2 over 2n squared, otherwise known as 1 over n squared. If I go to n equals 2, we're going to get a negative 1 plus a 1, so we're going to get 0. And if I go to n equals 3, I'm going to get a 2 over 2n squared. So I'm going to end up with 1 over n squared, otherwise known as 1 over 9, right? And this one, of course, is going to be 1 over 1. So the take-home message here is clearly the odds. The odd ends have the 1 over n squared, and then the even ends, well, they're just going to be, the coefficients are 0. All right, so if I move a little bit more up over here, if that's my takeaway formula, what I can really do is say that, well, we have the n, but we only need the odd ends. All right, so what I can take is my n, and I'm going to turn it into a 2n minus 1. Okay, that gives only odd values. All right, so that gives me a function f hat of x. Let's write it down now, and it's going to be the sum of n equals 1, because we're always starting at n equals 1, and we're going up to forever. And then we're going to have a 1 over, and now we don't put n squared. Now we're going to put, instead of n squared, we're going to put a 2n minus 1 quantity squared, and then we multiply it by our cosine of, and now we were doing cosine nx, but now we're going to do 2n minus 1 quantity times x. And that's our Fourier series. Okay, this looks pretty good. And now what I want to do is ask another question. So I want to ask a question about basically looking at this at the series. Can we deduce the zeros? Or at least, and we know the zeros, though. That we know that x equals plus or minus pi over 2. Because we determined that from the graph. We also looked at that algebraically. We find out it's true. But the question is, if I look at this, can I actually see those zeros? This is important in Fourier series because many times if we look at those zeros, they're also called the nodes. And those nodes can often be interpreted right from the series, and you can see important properties of the function by looking at where those zero crossings are. Okay, so let's actually see if we can figure this out. So I'm going to rewrite what I just had before. So I have f hat of x, and that's going to be equal to the sum from n equals 1 to forever of 1 over 2n minus 1 quantity squared times cosine of 2n minus 1 times x. All right, so we want to know when is this 0? Well, one thing we can do is basically examine when each of these is 0. And by these, I mean the cosine functions. Well, if there is a common x value such that the cosine of 2n minus 1 times x is equal to 0 for all n, then f hat must also be 0. Well, this seems like a pretty straightforward thing to do. Let's now move and give myself a little bit more space here. And again, I'm going to write down that function again. It's going to be 2n minus 1 times x is equal to 0. And n, of course, is going to run from 1, 2, 3, 4, up to forever, right? So we want to solve this. All right, so we have a 2n minus 1 times x. And we know that the roots to this on the entire x-axis are pi over 2. And then, of course, we have pi over 2 plus pi. And then pi over 2 plus 2 pi. And so on. And then, of course, also the negative of each. Okay, and we don't really need those negatives right now, because once we get the positive ones, we can of course just do a mirror image, right? And we already know the answer. It's pi over 2 plus or minus pi over 2. So we have to figure out why all the other ones go away. Let's see if we can figure this out, though. So really, though, we know, though, of course, that x has to be in 0. Undo that. Has to be within negative pi to pi. Okay. So what do we have to do then, of course, is look at this. We have to look at x and look at it as actually pi over 2 times 2n minus 1. And then, of course, a pi over 2 plus pi all over 2n minus 1. And so on. And so on for all of our terms, this one, and that one, and so on and go forth. One way to write this, though, is to actually look at it as the following, is that what we have here is we're going to write our x as actually an x of k, and we're going to write it as pi over 2 plus k minus 1 times pi all over 2n minus 1. And here, we're going to take k is equal to 1, 2, 3, 4, all those. And they basically just give us those multiples of pi, just like before when we put it in there. Okay? All right. All right. And so what we're going to do is, of course, let's simplify this a little bit. This is going to be pi over 2 times 2n minus 1, just like before. And then I'm going to add it as well, a 2 times k minus 1 times pi. And that we have it all under a nice common denominator here. All right. We can do a little simplification here. We can factor out the pi. And we can factor out the 2, and then we have a 2n minus 1 there, right? And then if I look what's left over, we actually have a 1 plus 2 times k minus 1. And we have a pi over 2. And if I simplify there, I see what I really have here is actually a 2k minus 1 all over 2n minus 1. All right. Well, that looks nice. And we know, of course, that this has to be within, well, let's actually just look at the positive side. It has to be within this range. Okay. Let's see if I can figure it out. So what I'm going to do now is I'm going to go to yet another page. So we have our xk, and our xk is going to be pi over 2 times 2k minus 1 over 2n minus 1, okay? And then n is, we're going to think of that as n, of course, is going to be 1, 2, 3, 4, and so on and so forth, right? And then, of course, k can also range from 1, 2, 3, 4, and so forth, provided that xk is still less than pi. Okay, well, let's see if we can figure this one out. And so we know, let's go back to our main problem again, right, is that we want all of these have to be 0. All must be 0. So they have to be 0 for each n. All right. Well, let's see if we can figure this out. What we have to do then is just start with, we're going to start with n equals 1, and then find the xk's. Then go n equals 2, find xk's there that are the same as for n equals 1, and then of course go to n equals 3, and so on and so forth, and just see if I can keep finding which xk's always are the same. If there are any different or new ones, it doesn't matter because they have to be common throughout all of the cosine functions for each n value. Well, this one should be pretty easy. If I have n equals 1, that's our starting point, then of course we're going to have, if I look at my formula up here, then we're going to have, we're going to start, of course, with k equals 1, and that's going to give us a pi over 2 times 1. Right, and if I were to go to a k equals 2, can I even go to a k equals 2? Well, let's actually just check. We know we have a pi over 2, and then we're going to have a 3 over 1. Of course, that's equal to 3 halves pi, which is greater than pi, so nope, we can't do it. We can't do that one on this particular case. Right, so now I go to n equals 2. Now I have, now I have a pi over 2, and now I have in the denominator, because I have that 2n minus 1, I put that in there, I'm going to get a 3. And now I'm going to do, of course, a k equals 1 again. I have a 1 there, and that, of course, gives me a pi over 6. Well, the only value we had for n equals 1 was pi over 2, and pi over 6 isn't that same value, but let's see if we can go. Now let's try a k equals 2. The k equals 2 value, so I've put a comma there, and now I have a pi over 2, and now, of course, I have a 3 over 3 for my factor there, and that's equal to pi over 2. It's still alive. It still exists, all right? And I could, of course, go to the k equals 3. I'll do that just to show what these other nodes are. Clearly, we're going to get a pi over 2 times 3, and then we're going to get a 5/3. And we can see this actually is a root of the n equals 2 function, because that's, of course, going to be 5 pi over 6, which is less than pi. So it's in our domain. The question is, can we keep finding pi over 2? And now we're going to do n equals 3. and I'll spare you the details, but if you go to k equals 3, of course, we're going to get a pi over 2 times a 5 over 5, which again is going to be pi over 2. We have it. In fact, we found out it goes if n equals k, then the xk root will always be pi over 2 for all n. So as long as you can keep finding these, and we certainly can, we know that the root, of course, is pi over 2. So x is going to be, our conclusion is x equals pi over 2 is a root to the Fourier series. All right, of course, we already knew by looking at the function we started with that that was what was going to be true. But do you see how by using the Fourier series, we're still able to find that root by just looking at the roots of each constituent function? And why we're doing this is that we're getting more and more comfortable manipulating these series, learning how to pick them apart carefully. I think it's a really valuable skill no matter what you do. All right, so I'll leave it at this, and I'll see you in another video.